morning, grade 10 students. We're then discussing some of the gas law showing the relationship of different properties of gases, such as the volume-pressure relationship, wherein they are inversely proportional to each other. It is described on Boyle's law. As the volume decreases, the pressure also increases, whereas the volume increases, the pressure will decrease. The next one is the volume-temperature relationship, wherein they are directly proportional to each other. It is described on Charles' law. As the volume increases, the temperature also increases, whereas the volume decreases, the temperature also decreases. Now, how about the relationship between pressure and temperature? The relationship of pressure and temperature was discussed on a gas law called Lussac'S Law. So for today, we will talk about the concept of Lussac'S Law, and we will use some mathematical equation to show their relationship. Lussac'S Law was proposed by a French chemist, Joseph Louis Gay-Lussac. Here is an example of pressure-temperature relationship of a gas. As the water is boiling, the temperature of a gas inside the kettle increases, and as the temperature continuously increasing, the force of a gas molecules also increases. One of the evidence showed that a gas exerted force in the kettle is when the steam is moving out of the container. So this is what happens to the air molecules inside the kettle before adding temperature on the gas present on the kettle. So air molecules have an initial force or initial pressure inside it. This pressure causes the air molecule to move, and as the temperature increases, the air molecule moves faster, causing it to move out of the container. Steam was an indicator that the air moves or the air molecules cannot be held by the container because of its high pressure inside it. So as the temperature increases, the pressure also increases. So Gay-Lussac's law states that if the volume is constant, pressure is directly proportional to the temperature. When we say directly proportional, as the temperature increases, the pressure of a gas also increases. Or, if the temperature of a gas decreases, the pressure of a gas also decreases. Now, let's plot the data of pressure temperature of a gas and show it in a graph. So let's say we have a gas molecules inside a fixed volume having a temperature of 10 Kelvin and a pressure of 0.50 atm. Experience a change to its pressure and temperature and have 20 Kelvin as the temperature and 1 atm for the pressure. Another change happens to the molecules inside a fixed container, and they have 30 Kelvin as a temperature and 1.25 as a pressure. So here is the summary of the data or changes experienced by a gas molecules present on this fixed container. Now let's plot it on a graph. So as you can see on the graph, it shows that the temperature increases from 10 Kelvin, it moves or it increases to 30 Kelvin. So temperature increases. As the temperature increases, pressure also increases. So from 0.5 or 0.50 atm, it changes into 1.25 atm. So pressure increases. If the volume is constant, the pressure is directly proportional to the temperature of a gas. Here is an example or real life example of pressure-temperature relationship of a gas. First one is the aerosol can. When an aerosol can is subjected to hot environment, the propellant gas inside gets vaporized. These vaporized gases exert the pressure on the wall of the bottle. The pressure on the wall increases with the temperature. Finally, the can bursts when the pressure becomes intolerable. This is the reason why it is recommended to keep the aerosol can away from the heat. Another example is that a firing of gun. There are mainly three components of a bullet. These are the primers, propellant or gunpowder, and a proper bullet. All of them are held together in a case or a cartridge. When a person pulls the trigger, a spring mechanism hammers the metal firing pin on the back end of the cartridge. Thus, this primer is ignited, which in turn ignites the propellant or the gunpowder. And this ignition generates a lot of superheated gas, increasing the pressure inside the bullet cartridge. Hence, as a result, a bullet is fired from a gun, leaving behind its cartridge. Now, let's use some mathematical equations to prove the relationship of pressure-temperature relationship. If the volume is constant, pressure is directly proportional to the temperature. So pressure is directly proportional to temperature, and that is constant. It is always constant that the pressure is directly proportional to the temperature. So we will have this equation. Pressure is directly proportional to temperature, and they have a constant relationship. Now, if we will have, or if we will substitute this equation to leave the constant sign or constant symbol on one side of the equal, we need to divide both sides to the symbol or the quantity beside it, which is the temperature, to cancel out the temperature, and we will have this equation wherein it is constant that the pressure is directly proportional to the temperature. So if there is a change happens on pressure and temperature, still it is constant that the pressure is directly proportional to temperature. Now, to come up with the equation, if one quantity of pressure and temperature is unknown on one word problem, we need to use this equation wherein we need to cross multiply the product or the quotient of pressure and temperature, or the initial pressure and temperature, to the quotient of the final pressure temperature. And if we will do that, we will come up with this one, wherein initial pressure multiply, or the product of initial pressure and final temperature is equals to the product of final pressure and initial temperature. So this equation is being used to identify if one quantity of pressure and temperature is unknown on one word problem. Now, let's take this equation on a word problem. So let's say the pressure of a nitrogen gas inside a reagent tank is 1.5 atmosphere at 30 degrees Celsius. What will be the resulting pressure if the tank is cooled to 0 degrees Celsius? So first, let's identify the given quantities on this word problem. So we have 1.5 atmosphere, which is our initial pressure. We also have the 30 degrees Celsius, which is the initial temperature. We also have the 0 degrees Celsius, which is our final temperature. Now remember that if there is a temperature involved on a gas, we need to always use the Kelvin scale instead of a Celsius scale. It is because Kelvin scale have the what we call the absolute zero, or the state of a gas wherein there is no energy left on the gas molecules, or they have a limit for the energy for a gas molecules. So for this temperature, we need to convert it into Kelvin, and to do that we need to add 273.5 to come up with a Kelvin. So 30 plus 273.5, we will have 303.5 as the Kelvin equivalent for the 30 degrees Celsius. For the 0 degrees Celsius, add 273.5 and we will have 273.5 Kelvin. Now let's identify the unknown quantity. So for the given, we need to identify which is the missing quantity for this work problem. So we have the initial pressure, we also have the initial temperature, and last we have the final temperature. So the one that is unknown or missing on this word problem and being asked on this word problem is the final pressure. So we need to identify the final pressure. Now let's use an equation to identify the final pressure, and to do that we need to divide both sides of the equal with the quantity beside the unknown one, and the quantity beside final pressure is the initial temperature. So we need to divide both sides of the equal with the initial temperature, so that initial temperature will be cancelled on one side of the equal, and we will have this equation wherein pressure or final pressure is equal to the product of initial pressure and final temperature over initial temperature. Now let's put the amount for each quantity. So we have the initial pressure, which is 1.5 atmosphere. We also have the final temperature, which is 273.5 Kelvin. We also have the initial temperature, which is 303.5 Kelvin. So first we need to get the product of final temperature and initial pressure. So 1.5 multiplied by 273.5, we will have 410.25 atm Kelvin over 303.5 Kelvin. Now we need to get the quotient of the two. So we need to divide 410.25 to 303.5 and we will come up with the answer of 1.35 atm. Now we need to, or we have this atmosphere. It is because the Kelvin is being cancelled on this equation. So we have a unit of atm, and also because we need to identify the pressure, and the unit for, or one of the unit of pressure is atmosphere. Now let's take a look if what will happen to the pressure and temperature on this word problem. So we have an initial pressure of 1.5 atm and a final pressure of 1.35 atm. Now what will happen? Is there an increase or decrease of a pressure? So as you can see, from 1.5 to 1.35, there is a decrease happens on the pressure on this word problem. How about temperature? So initially we have 303.5 Kelvin as initial temperature. We also have the final temperature, which is 273.5 Kelvin. So what happens to the temperature in this word problem? So as you can see, from 303.5 Kelvin to 273.5 Kelvin, there is a decrease on the temperature. So just like what Lussac'S states that at a fixed volume or a constant volume, they are directly proportional. So if pressure decreases, temperature also decreases. So for the Lussac'S law, always remember that if a volume is constant, pressure is directly proportional to the temperature. So as the temperature increases, the pressure will also increase, or as the temperature decreases, pressure also decreases. That's it for our discussion for today. Thank you very much, great students.